Hey everybody, Chris here with a little tutorial in Fusion 360. The other day, John over at NYC CNC did a video on corner reliefs in parts with non-circular holes through the center, like in this model right here. I'll put a link to John's video here in the upper corner, but John did a really good job of explaining like why you would, or I guess how you would put a corner relief in an area where you've got a non-circular hole going through a part, because round tools like end mills and things cannot create these sharp corners like you see right here. In this case, we've got a really simple, it's just a little linkage. You rotate the shaft and the link moves with it. You could also slide this link along the hex shaft, or it's in a little simpler case, you could also do the same thing with a square shaft. If you really needed to transmit torque somehow to a link, and this could be connected to some other mechanism along the way, but the real problem here is it was very easy to create this square hole in this arm, but how do you actually produce this from a manufacturing perspective? Now, something I saw in the comments on John's video was people said, well, why didn't you make the model look like what the finished part was going to be based on the manufacturing method? Or maybe in a case like this, you could buy a square broach and you could broach the square hole and have your nice sharp corners and everything. Or you could buy a hex broach. These are perfectly viable ways of making a non-circular hole, but not everyone always has access to those types of tools. And so if you're just a guy with a Bridgeport in his shop and you need to make this part, other ways you could do this is wire EDM or just a straight up EDM machine. Perfectly viable ways of manufacturing this, but if you're designing this part or manufacturing it, you have to take into consideration the equipment that you have. So if you have something basically, just like I said, a straight up milling machine like a Bridgeport or even a CNC milling machine, as John put it, Mickey Mouse corners, or I guess more generically, a corner relief is a good way to have a non-circular hole in a part to allow a non-circular shaft to engage with the part, with the hole. So John had a really good method for creating those corner reliefs, or the Mickey Mouse corners, for figuring out what size drill you need to pre-drill the corners before coming in with an end mill to clean up and finish off the corner. I thought John's method, while it was pretty good, it didn't take advantage of certain tools within the sketching environment here in Fusion 360. So what I wanted to do was show you a little different way of approaching that problem of figuring out what is the smallest drill size you can get away with in this corner to pre-drill it prior to using the end mill of the size that you would like to use to finish the hole. So I'm going to start with the square part here, and this was a part I created earlier. I'm just going to go ahead and open this part up so I can modify it, and then when we come back to the assembly, you'll be able to see how that the corner reliefs I put in here engage with the shafts. So the first thing I'm going to do is I'm going to go in on this front face and I'm going to create a sketch, and I'm going to come in here, and the first thing I like to do is draw the end mill, or a circle to represent the end mill that I'm going to use. So I'm just going to go in here, draw a circle. I'm going to give it a dimension. In this case, I'm going to say we're going to use a 3/8 diameter end mill. Now the other thing I'm going to do is I'm going to make this a reference circle, or a construction circle, by selecting it and pressing X. I'm going to add a tangent relation or constraint here to of the circle to the edges of my square hole, because this is the farthest into the corner that the end mill can possibly get to for a 3/8 end mill. If I were to change the diameter, of course it would move closer to the corner. If I go smaller, further away from the corner as I get larger with the end mill. Determining what size end mill you use is, it's kind of your preference. The bigger the end mill you use, the greater the material removal rate will be, the faster you'll be able to cut the hole, but it also means that you'll have a little less flat on each side to engage with the shaft. And from a design standpoint, that's up to you to determine how much flat you need engaging with your shaft to transmit the torque that you need. And so that will really be your determining factor for the smallest end mill. But what we're after here is what's the smallest drill size for a given end mill. So we say we have a 3/8 end mill here. So the next thing I'm going to do is I'm going to draw a circle here. But actually, before I do that, I'm going to create a couple of points. First point I'm going to create, I'm just going to go over here and I'm going to put 2 points, one on each of the sides. They are coincident with the edges. I'm going to also make that point coincident with the circle so that it becomes connected right at the tangent point of the circle. That's going to be our end mill to the line. I'm going to do the same thing up here on the top. The next thing I'm going to do is I'm going to create a circle, a 3-point circle. I'm going to choose that point, the point I created over here, and the corner point of my square hole. Now, the next thing I'm going to do is I want to create a dimension on that circle. And you'll notice that Fusion comes up and says that this will over-constrain the sketch. And that is true because I've defined it based on the other geometry, and I can't actually control the size of this hole with this dimension because it would violate the other constraints. So I'm going to make this a driven dimension by choosing OK, and you'll notice it's in parentheses. So that, in this particular case, this would be the smallest drill size that I could pre-drill the corner of the hole with to allow us to use a 3/8 end mill to have flat sides on each corner. Now, as one thing John mentioned in his video is that you wouldn't necessarily want to have this circle coming exactly to the theoretical corner of the hole. And that's a very valid point, because if the shaft is machined, or if the shaft is a little oversized, or if this hole was machined a little bit out of tolerance or whatever, you could have an interference of the shaft going through this corner clearance here. And so you want to give yourself a little bit of room. Or if your drill is a little bit undersized, it's you end up with you could have an interference. So at least we know that 0.265 here is the smallest diameter drill, and that's I think a number 71 drill. I could be wrong about that. That could be way off, but we can at least go over to a drill chart and see what size drill corresponds roughly to this diameter, or at least gets us in the ballpark. But in order to provide the clearance we want in the corner, there is a few more techniques here that I'd like to show for how to give yourself a little bit of clearance over here on the edges, so that you can make sure that your end mill will totally clean up the straight edge and also provide the clearance over here that you need for the corner of the shaft that's going to be going through. So what I'm going to do right now is I'm going to delete this circle that I created. I'm going to leave these 2 points that I created over here as well, and I'm going to create 2 more points. Maybe we'll go to sketch, point, create another point over here on the line, create another point over here on this line that's coincident, and now I'm going to create another 3-point circle. So I'll go to circle, 3-point, I'm going to choose the point I created over there, the new point I created down here, and I want to create some point over here in space that's a little ways away from the corner. Now the next thing I'm going to do is I'm going to create a line going from the corner out to my circle. I'm going to make that line a construction line by selecting it and pressing X. I am also going to create a line going from my original tangent point from my ML out to this new point. I'm going to create a line down here going from this tangent point out to this new point. I want to select that line and the other new line. I'm going to make both of those construction lines by pressing X. And I'm also going to select those two lines again and make them equal to each other, so that as I change the size of the circle, the points down here will move around equal distance from the tangent points on the end mill. Now what we want ideally is we want the new point that we created that the drilled hole circle passes through to be just to the left of the tangent point, or just below the tangent point of the end mill going in the corner, to ensure that the end mill will come off of the edge created by our drilled hole. Now the other thing I'm going to do here is I'm going to make my clearance at the corner here equal to my overshoot here on the ends, just to because I want to minimize the size of the hole that I'm drilling to maximize the length of engagement I'm going to have over here on the finished edges. So I'm going to choose the equal relation, or select this line, choose equal, make it equal to one of these other two edges. And you'll notice those lines adjusted. The final relation I need to put in here, or constraint I need to put in, is a coincident constraint between this line and the center point of my drilled hole, so that this will be at a 45-degree angle relative to the corner where we're drilling. So as you see that I drag the circle around, you'll notice that all the clearances on each corner are all moving equally. I should put a dimension on in the corner to say that I would like, say, 15 thousandths, no, not 150 thousandths, I want 0.015. 15 thousandths clearance at the corner, but I'm also going to have 15 thousandths clearance over here and 15 thousandths clearance over here that the end mill will go past where my drilled hole intersects the side wall. So we'll ensure that we're going to totally clean off this edge right here. And then I will add another diameter dimension to my drilled hole circle. Again, Fusion tells me that I'm over constraining the sketch, which is true, and I want this to be a driven dimension, which it says that it is 0.288 inches, which is slightly over 9/32, a little bit bigger than a quarter of an inch. But let's say I want to use an actual 9/32 drill. Well, I can't just go in and change this dimension because it is a driven dimension driven by other parameters. So one thing that I can do now to get me to my actual drill diameter that I do want to use, an exact value, is I can change my clearance dimension over here by right-clicking on it and toggling it to be driven, and going to my drill circle diameter, toggling it to be driving. And now I can change this to 9/32, which is 0.28125. And now you'll notice that the clearance over here at the corner, which also corresponds to the clearance over here on the edges, is now 11 thousandths for using a 9/32 drill. I can live, I think, with 11 thousandths clearance over there on the edge. If I wanted more, I could change this drill diameter to, say, 5/16, 0.3125. Now you'll see I get 30 thousandths clearance all around. And in doing so, I'm just going to go with this 5/16 drill corner. I'm going to complete my sketch. And now what I would like to do is I would like to cut out that corner because that's how the finished part is actually going to look. It will have that corner drilled out. So I'll go to my Create menu, Extrude. I'm going to extrude that profile to the far side. It's going to be a cut as indicated down here because it turned red. And I'm going to hit OK. And now you'll notice we've cut out that corner. The next thing that I can do is I can actually, because this is square, if it can be rectangular, doesn't really matter. In this case, because it's square, I'm going to cheat a little bit and I will go to the Create menu, go to Pattern. I'm going to do a circular pattern. It's going to be a pattern of a feature. I'll choose the feature that's extruded cut down here in the timeline. I'm going to choose as my axis the blue axis here. There are 4 corners to this hole. And then I'm going to hit OK. And now you will see I have my 4 corner reliefs in here in my square hole. And this is what the finished part is actually going to look like. If I were to go back to my sketches and turn on the sketch I created, you'll see here that there's my 3/8 end mill circle right there, and it will completely clear on all 4 corners, and we'll be able to create our hole that a square shaft will fit into. Now, if I switch back over to my square shaft assembly and turn the shaft back on, I will need to update my square holed arm here. I'm going to save it, switch back to the assembly. Fusion is telling me that one of my components is out of date in the assembly, which is true. So I will update the component and it'll grab my recent save. And now you can see when I look here at the end of the part, you will see that I have those square corners, and I will have 30 thousandths of clearance here in the corner between my shaft and the hole that is in the part. And that would be what the final product would be as produced on the milling machine. For very common practice, I do this all the time in my day job and working with the equipment that we have in our machine shop. And one of the greatest things you can do is to try to help your machinists. If you're not the person who's going to be making the part, you got to think about the person who is and the tools that they have available to make the part that you're trying to design. And so if you've taken the time in designing your part to think about the tools that are available to the shop that's going to be producing your parts, the people making it will appreciate your efforts because it makes their job a lot easier in determining what size tools they need to use to ensure that the part can actually be made. And Fusion makes it really easy to design parts that can't actually be produced. And design for manufacturability is very important. And thinking about this kind of thing ahead of time can be the difference between actually getting your part made and not. So very similar technique can be employed in the case of the hex shaft. And that was the case that John had looked at in his video. And so I'm going to open up the hex shaft arm here. Very similar procedure. I'm going to select one of the faces here. I'm going to create a sketch on that face. I do the same thing I did last time. I'm going to create create a simple circle here on the inside. That's going to be my end mill. I'm going to dimension that. I'm going to make it in this case, I'm going to make it a 1/4 inch diameter end mill. But I also make this a construction circle. I'm going to make it tangent to my sides of my hex. I'm going to create a couple of points at on each side of the hex. I want to make those points coincident with the end mill circle as well. I want to create 2 more points out here on the hex, just like I did before. I'm going to create a 3-point circle between those 2 new points and a 3rd point in space. I'm going to create a line from the corner of my hex out here to the arc. I want to make that a construction line. I'm going to create a line from this point to this point. Create a line from this point to this point. I'm going to select those 2 lines and make them construction lines as well. I'm going to make those 2 lines equal to each other. Also going to make that line and that line equal to each other. Looks like I'm going to have to drag this point around a little bit. Finally, I'll create a coincident relation between this line and the center of the drilled hole circle. I don't think that actually took. Coincident line point. There we go. That's what I wanted. And then I will create a dimension on my corner clearance here. I want it to be 30 thousandths. We create a dimension on my whole circle here, which is going to be driven. Like it's going to be 178. Well, I'd like to use a 3/16, which is 0.187. So I'm going to switch this dimension to be driven and switch my diameter to be driving. I'm going to change it to 0.1875. That gives me 36 thousandths clearance here in the corner. And of course 36 thousandths overhang here on the sides. I suppose I could actually change this down to 0.1565, another common drill size, and it still gives me 15 thousandths. I guess I can live with that. So we're going to use this size drill bit in the corner with our 1/4 inch end mill. Stop my sketch and select that profile. I'm going to extrude that profile through my arm here up to the far side. It's going to be a cut. We'll say OK, and so now you'll see we have that corner relief in there on that corner. Again, I'm going to create a circular pattern of that feature by choosing that down here in the timeline. I'm going to do that around this axis. There are six corners here, so we shall adjust the quantity to 6, press OK. Now we have 6 corner reliefs. And I will say save. And then I'll switch back over to my hex shaft assembly. It's telling me that one of the parts is out of date, which is the arm. I'll update that part. And now you see we have the corner reliefs for the hex. And then the corner of the hex shaft will now clear the corner by, I think it was 15 thousandths over in the other model. So I hope that this video helps you understand why you would actually put this type of corner relief into a non-circular hole to work with non-circular shafts, and hope that the techniques shown here in the sketches in Fusion will help you determine the size of your drill bit based on the size of the end mills that you have available, that you choose based on thickness of material, and how much flat you want to have on each side of your hole to engage with your non-circular shaft. Please leave a comment below if you have any questions, and if not, we'll see you next time. Thanks.